Okay, good evening, everyone. Hello, am I audible?
Yes, sir, you are audible.
Okay, thanks. Uh, okay, so this is the first tutorial of introduction, a brief introduction or brief course on superconductivity. I welcome you all. Myself, Sunit Das, PhD scholar from IIT Kanpur, and yeah, so we'll primarily be doing some problem solving in these sessions, but that depends on what you people want actually. Because I'm seeing the assignments, these are assignments are mostly from what has been taught already or what has been derived in the classes, right? So yeah. So before starting, let me know what do you expect from this tutorial session because that will help me to organize and yeah, prepare at least from the next classes. So please unmute yourself and yeah,
Good evening, sir.
yeah,
This is Shashi Kumar from National Institute of Engineering.
yeah.
Sir, this is the first tutorial class, right?
Sorry.
This is the first class you are taking, right?
Right, right. This is the first class.
Okay.
So, any specific questions or yeah,
Sir, this course is related to automation, right?
not really. This is related to the superconductivity.
Superconductivity, in the sense, this is not related to automotive field or automation.
No. So,
Okay.
everyone here is from the superconductivity course, right? Can anyone confirm?
Yes, yes.
Okay. Let me join with another device and then I'll start. Yeah, I mean you can leave actually because this there is nothing automated and so on and so forth. I mean, yeah. I think Sasi Kumar.
Yes, sir.
Okay.
Thank you, sir.
Okay. So everybody have seen the. Let me. How do I minimize this screen? So anybody knows how to maximize the screen, the white screen? Let's try. Hello. Let me stop. Sorry, I just got disconnected. Hello. Yeah, sorry, I just got disconnected. But yeah, uh, the screen is not visible. Okay, so everybody can hear me? Hello.
Yes.
Okay, but you don't see the screen, right?
No. Screen is not visible.
Just a second. Sorry for this initial problem. I think the screen is not getting visible. Still screen is not visible. Just a second, please. Huh? Okay, I think now it's visible. Okay, so do you have any specific questions to begin with? Because this is mostly doubt clearing sessions, and I'll partially be doing some questions or answers, let's say. Those are kind of related to the what has already been there in the assignments. But yeah, so anyone have any particular questions?
Right now, I don't have any specific question. So
Hmm.
I think I don't know about the others. So from my side, you can start what you have planned.
Okay, okay.
Good evening, sir.
Yeah, good evening.
Sir, assignment has sent, but I have doubts that how we can send the answers for NPTEL.
Yeah,
Same in the mail.
assignment answers should be uploaded in the NPTEL, right? I mean portal.
Yes, sir. How we can do that, sir?
So you just uh, write the solution and scan, and there will be a I mean, so there will be some option to upload. Just you just click there and upload your solutions in PDF.
Okay, sir. Thank you, sir.
Okay. So any other questions? Yeah, I mean you just unmute and tell the questions. Uh, this I do not know actually when assignment marks will be released, because this is generally I think NPTEL does this in consultation with the professor. Okay. We TAs do not see the assignments, I mean the assignment solutions. Okay. Yeah. So yeah, so please unmute yourself and tell, so that I mean chat is typically difficult to deal with. Okay, okay. Okay, so let me start by just giving the brief introduction and then we can go to the specific problems. Okay. So this is the first day, so there might be some hiccups in the connection and in the delivery, but I hope in the next day or the next 3 4 days it will be more sort of uh, engaging. Okay, so what do you know about superconductor?
Sir,
Yeah.
sir, actually, I was not unable to submit the assignment zero because of some internet problem. Then I next day I mailed and
Hmm.
they replied it's not possible for me to supply again to submit it. Is there any problem in future? I am confused about that.
Not really, because assignment zero was anyway need not be graded. Uh, so it was just there to familiarize with the things,
Okay.
how
But
to upload
I have completed my assignment, but some problem due to some problem I have not uploaded that. And then
uh,
next day I mail for that. But they
this is
from
about
that
assignment one or two. Sorry, zero.
zero, sir. Assignment zero, sir.
Assignment zero is fine. If you are able to upload that, it was fine actually. So this was just to familiarize ki how to upload and things like that.
Okay.
So from
Okay.
assignments one, things graded, grade will be counted.
Okay. Okay. Thank you, sir. Thank you.
Okay, so let me start. So superconductivity. Uh, so in 1911, actually, Kamerlin Onnes, physicist working with mercury and many other materials actually. He was lowering the temperature of mercury. So mercury, we know it's a conducting metal type behavior it shows, and he was observing the resistance as a function of temperature. Okay, and these all temperatures that we'll be talking about in the superconductivity course are in Kelvin scale, not degree Celsius or Fahrenheit. So what he observed is that initially it was sort of as expected for metal. As you increase the temperature, so suppose you have a metal, you are increasing the temperature, the resistance also increases because there is more electronic collisions, and the electrons flow get disturbed by the temperature, thermal energy scale, and so on. So the heat is also there in the metal, so resistance increases. Basically, in other words, the ability to conduct freely, ability to conduct free electrons is basically decreases, right? As you increase the temperature. So that's what it happens. So let's say you started from here and you are decreasing the temperature, that means resistance also decreases. Now around very low temperature actually, it was almost 4 Kelvin. So 4 Kelvin, something dramatic happened. The resistance dropped sharply and it was almost immeasurable. The resistance was almost immeasurable. So there might be some resistance here. Uh, it's pretty low, almost near zero, but at that time it was almost zero. The sensitivity of the device was like that, it was showing zero almost. So this is the first kind of observation of phenomena called superconductivity, where the resistance of a metal goes to zero at some um critical temperature. For mercury, it was 4 Kelvin. For any other materials, it will be something different, and so on. And that also depends on the material properties, right? So this was the first, I mean, birth of superconductivity kind of. There are many theories that try to explain that. Even this superconductivity is still today one of the most, I mean, active topic in condensed matter physics. On more particularly, I mean, successful theory is the BCS theory, which started around 1956, I think, and then yeah, so around 1950s and 1960s it was formulated. So Bardeen, Cooper, and Schiffer. So these three guys worked together to formulate a BCS theory. BCS theory is pretty much mathematical. So we'll go, I think in the next class we'll go about BCS theory. more detail. But today I plan to cover basic phenomenology of superconductivity. Let's say often we call it electromagnetism of superconductivity. Okay. Okay. So the first thing superconductors shows is that of course the resistance is zero. Sorry. So resistance is zero at some particular temperature, T equal to Tc, critical temperature. And the second most important, and this is the most important experimental test, that a metal in the low temperature regime is indeed a superconductor or a very good conductor, is that Meissner effect, right? Meissner effect. So what really happens is that suppose you have a material and you lower the temperature. So you lower the temperature T below Tc. At Tc, this material becomes superconductor. Uh, and then, so now it is superconductor. This was some material. Then you apply magnetic field. Now, what superconductor really does is that it do not allow magnetic field to penetrate this material. Okay. So there is no magnetic field inside the material if it becomes superconductor. Now you can do the things other way around. So you have a material which you know that it is going to be superconductor at some temperature below Tc. You initially apply the magnetic field B not equal to 0. So so your material is having some magnetic field inside it, but now you lower the temperature T less than Tc. You again get back the same situation that I mean there is no magnetic field within the material itself. So it just crosses outside the material. Okay. So this particular phenomena is called perfect diamagnetism. So what does it mean by diamagnetism? It is just the tendency uh, to to not be influenced by the magnetic field, kind of, you can say. So if you have a paramagnet, let's say, and you apply magnetic field, then it has a tendency to I mean the magnetic field can easily penetrate the material. But for diamagnet, it will try to repel the magnetic field actually. Okay. So this is just the opposite of paramagnet. So yeah. And typically normal metal shows diamagnetism where this susceptibility, which is magnetization with respect to the applied magnetic field. So in this course, H and B will interchangeably use. So H just means the applied magnetic field, and B is also the magnetic field. We'll use in the same sense, but they are used. They are related by this. Of course, there will be magnetization and so on. In free space, this is the relation. B equal to mu h, mu 0 h. So this is the susceptibility that you apply some magnetic field H, and how it can get magnetized, how much is the susceptibility to be magnetized, right? Now for paramagnet, it is some positive number, so it is definitely greater than 0, which physically means that if you apply magnetic field, external magnetic field, the natural tendency of a paramagnet is to be magnetized, right? So there is a orientation of magnetic moment along the same direction, let's say, and so that it becomes magnet under the influence of magnetic field. But diamagnet is something opposite. It will oppose the effect of magnetic field, let's say, so that chi becomes 0. Sorry, less than 0. Okay. For typical metal, chi is actually of the order of 10 to the power minus 3. It can also go to 10 to the power minus 6 for some materials. Okay. So it is a very weak diamagnetism. But for superconductors, it's a perfect diamagnetism. So you have a relation B equal to mu 0 H plus M. So the effect, you apply H, and inside P is absolutely zero. So you have mu 0 H plus M. Okay. So that's how you can show that chi equal to del M by del H equal to -1. So this is the perfect diamagnetism. Now, so this is the actually true litmus test for superconductors, that it shows Meissner effect and the diamagnetism is perfect. Now, you contrast this with the perfect conductor. So suppose you have a perfect conductor, I mean very good metal, so to say. You lower the temperature. Uh, so for a perfect conductor, there is no such thing called critical temperature. For a superconductor, you have a critical temperature below which it becomes a superconductor. But so you basically go to a very low temperature. Okay, so T is almost near zero. Now you apply magnetic field. So B not equal to zero. Okay. Now it will also kind of repel the magnetic field. Okay. Now if you turn off the B, so now you turn off magnetic field, it just becomes the same. So this was, let's say, initial state. So this was initial state and this is final state. Okay. So it came back to its previous position. So we had a one material, I mean very good metal, let's say. You lower its temperature to almost 0 Kelvin and then apply magnetic field. But because of some, I mean, diamagnetism that the metal shows, it will repel the magnetic field. And then once you turn off the magnetic field, it just goes to the previous metal's state. Now, if you do the same process, I mean, a little bit differently, as we did for this superconductivity case, that you apply magnetic field first, so B not equal to zero, so that I mean you have some amount of magnetic fields growing through the material, and then you lower the temperature T less than Tc or T nearly equal to zero, let's say. Okay. Then also you will see that the magnetic field is going to be penetrated through the material. Now you turn off the magnetic field. You see there, you will observe there is a kind of shielding current that will flow, because it just follows from the conventional electromagnetism that any change in magnetic field is going to be resisted, Lenz's law, and so on, right? So there will be a kind of shielding current that will flow, which will oppose the change in magnetic flux. So these two state, so this was first state and this was the second process. We are coming back to the same situation, right? So we started with the material, and in the first process, we lowered the temperature, uh, turned on the magnetic field, and then eventually turned off the magnetic field. And then in the second process, also we did the same, but in a different way. We initially turned on the magnetic field, lowered its temperature, and then finally turned off the magnetic field. But you see, these two states are different. So one is going back to its previous metal states, this one, and in the second process, you are not getting back the previous state. It is having some shielding current, right? And this is the difference between a superconductor and a perfect conductor. But what is the similarity? Similarity is that a perfect conductor, if you really go near zero temperature, you will also have very low resistance, actually. In fact, it can show like superconductor like resistance, very low. But then there are many other aspects which you will not see in perfect conductor. For example, the CV that we will talk about later, the CV versus temperature, you will not see jump in this perfect conductor. Okay, those are the also other tests, but this is the most important test. Just by applying magnetic field and seeing how it behaves under low temperature, you can tell that that material is perfect conductor or it's a superconductor. Okay, so any questions? Okay, so since these are doubt clearing classes kind of, so please feel free to ask questions. And if you have any uh, complications regarding the solution of the assignment also you can ask me. So because so the only interaction that you're having for this course or for any NPTEL course is only that during this tutorial session. Okay, so how does this susceptibility route looks like for a perfect conductor? So we have M and then H. So we saw that M is just equal to minus H, so that uh, chi, which is del M del H, is equal to minus 1. So it is just a straight line. Okay. Okay. So now let's get back to the electromagnetism of superconductors and perfect conductors also. So initially, let's start with the Drude model. Okay, so Drude model we have seen in the first chapter of Ascough-Norman, which is to explain the origin of resistance, right? So this was for a normal metal that let's say we apply electric field, and there are some free electrons roaming around in the metal, and so what is the effect of this applying this electric field, right? So we have a p is the momentum of the electrons, so p is just electronic mass times the velocity, and this is equal to the force due to the application of electric field. And then there is a scattering that happens with the electrons with the ions that is present in, sorry, in the material. Okay, and so let's say here is one ion, there is a big material, and then electrons are there. So this is a very simplified picture, but sorry, yeah. So there randomly some ions are there. I mean periodically arranged, of course, in a solid state material, and then we have a lot of free electrons, right? So these electrons actually scatters randomly to the ionic cores, and that creates a kind of effect that is captured by this p by tau. What is tau? Tau is the distance between, suppose an electron uh, scatters here directly, okay, then it comes here and then scatters here. So this is the time difference between two consecutive scattering is the tau. Okay, so this in the Drude picture we assume it to be uniform for the material and for the electrons. Tau is constant, but for advanced theory we can actually calculate tau, and it is not a constant. Okay, okay. So this is the effect of electric field. Now at some point of time, so uh, the electrons will going to reach steady state. So then it will be dp dt equal to 0. So steady states means there is no acceleration for the electrons, right? And then p will be minus e tau electric field. So this will be the momentum. Now you contrast this with the now you get this momentum, and then so basically so this will be mev, and this is the drift velocity we call in the Drude model. So minus e tau electric field. So this, from this we can derive the velocity of the drift velocity of the electrons, and then can determine the current density, right? So current density is nothing but the n is the number density of the electrons present in the metal, let's say, and then charge minus e, and then vd, root velocity. So this is the current density. So current density means current passing through per unit area, right? And from this we get the Drude current to be so n minus e, and vd is minus e tau electric field by m, because so this m goes there. So this give rise to n e square tau by m electric field, right? So this is the current density related to the electric field. So we also know that J equal to sigma E. Sigma is the conductivity. So conductivity for the Dude model becomes Ne square tau by m. So this is for a conventional metal. You have a conductivity which depends on the number density of electrons, electronic charge, what is the scattering time scale, and then Me is the electronic mass. Okay. Now let's see what happens for a superconductor or perfect conductor. So for a perfect conductor, so this particular equation, so this equation, let me call it 1. So equation 1. So we had dp dt equal to minus E times electric field minus P by tau, right? Now for a perfect conductor, there is no collision. Electrons move perfectly freely, so that conductivity is also pretty high, right? So for a perfect conductor, tau is going to infinity. So there is no collision and the system is pretty, I mean, absolutely clean. So perfect conductor or superconductor. So that means from this expression, you can think that sigma is almost tending to infinity because tau is also tending to infinity. Okay. So from this Dude model, you can see already that for a perfect conductor, if tau goes infinity or superconductor also tau goes infinity, so conductivity becomes infinity. Okay, now let's look at the I mean this current density equation from a different perspective. So NEV, this is the general expression we have, and V we had NE. Uh, so the expression of V was, yeah. So if tau goes to infinity, then we have dp dt equal to minus E electric field. That means velocity will be minus E electric field by m, right? So minus E electric field by m. So this gives me, or rather I can start with dp dt actually. Yes, so I have dp dt equal to minus E electric field. Now we had a relation that J equal to, so J equal to NEV, and this we can write it as a, from this expression we can write MEdV dt equal to minus E electric field, right? So this J will be Ne, or rather I should write J dot actually. Just a second. Yeah, actually let me start with J. I think it is better. So minus E N V. So this was our J. Then I can write this V as minus E, so minus E N, and then dP dt by ME, right? So this is the, so because P is just MEV, and then I can determine, also we have P equal to, so this is equation number 1, and then we also have P equal to minus M by NEJ. So this is again just from this equation. Okay. So if I take derivative of this equation, dp dt equal to minus m by ne dj dt, right? Okay, so now I have this equal to, so okay, we have equation 1 as a dp dt. So I'm trying to find dp dt from here. So this, from this part, dp dt will be minus me by enj. So minus me, so all are me actually, electronic mass, ne. Something is actually wrong. I should get squares. Just a second, hold on. So we had dp dt equal to m by ne dj dt. Sorry, it's something wrong. Yeah, actually, the solution that I prepared is wrong. So I'll complete this in the next class. Yeah, the solution is pretty straightforward. It is wrong here. But what I was trying to derive is that, so it will be provided in the next class. So what I was trying to derive is that if you apply, let's say, a magnetic field, what I was trying to see in the Meissner effect, so you'll get some equation like b dot alpha. So alpha is some constant. So for example, alpha square actually come out to a MEN square mu zero. Mu zero is the permeability. Okay. So this is for time varying field. So B dot, I mean, means B has a time dependence. So this is valid for a perfect conductor. Okay. And how it depends, so as you apply magnetic field, a time dependent magnetic field, from this equation you can actually derive that how magnetic field penetrates within the material. Okay, so that was the motive of doing all this, but it will be completed in the next class actually. And if you solve this equation, so this equation solution in general is very difficult unless you have a particular profile of magnetic field, let's say. Okay, but one particularly easy solution is, let's say you assume magnetic field applied in, let's say, only x direction or unidirectional. So you have a b of x which varies in space, as well as it will have some time dependent field, I mean effect. e to the power I omega t harmonic. So for general B, it's really difficult to solve this equation actually analytically. Only harmonic and few other cases you can solve this exactly. So if we have this kind of m- I mean magnetic field profile, once we apply, then you can show that B of X. So how much magnet I mean, so you have applied magnetic field in a material, let's say. Now how magnetic field penetration or inside the material, how it depends actually. Okay, so you'll find that Bx is almost equivalent to B0, some magnetic field, and e to the power, so this is actually b0, sorry, this will not be b0, so this is b of x, and this will be, so this will be in unit of magnetic field, but this will also depend on the material properties actually, and it will be minus x by alpha. So what we will see is that for a perfect I mean conductor, the magnetic field penetrated within the material exponentially decreases. So initially, let's say just outside the material, magnetic field was whatever you applied. So this one was there, and then as you increase, I mean, as you go inside the material, it just exponentially decreases, and the decrease length scale is alpha. So this is the length scale. So it depends on the I mean electronic mass, number density, and the permeability. So here in this case we have assumed that material's permeability is mu 0, but it may not be mu 0, it will be some mu. So mu 0 is mu 0 into mu r. Mu r is the relative permeability with respect to air, let's say, or free medium. Yeah. Okay, so that's how kind of perfect conductor you can contrast also that I mean within the perfect conductor there will be some penetration of the field. Okay, so if you have any questions from the assignments, you can ask, or maybe I can go through the assignment and solve some problems, I think. So anyone have any suggestions or
I think you go according to your plan. As I said earlier, I don't have any specific question.
so the assignment problems was, so let me open. Okay, so you cannot see this screen actually. So let me write the assignment problem. I think that will be better. So I'll not fully solve the assignments because the same thing needs to be uploaded in the NPTEL, and it's a part of grading scheme. But yeah, just some hint. And so the first assignment is for a type 1 superconductor. Find the jump in entropy and specific heat across the transition from a superconductor to a normal states. So we need to find the jump in entropy. So let's say S is the entropy, and Sc is the entropy for superconductor, and then S, let's say normal. Normal is for the normal metal, normal state or normal metal, let's say. And then similarly, we can define, we can denote specific it as CV, uh, CSC, let's say, just, and then C, normal. So these are the entropy and this is the specific heat. So we need to find the jump, meaning SC minus S normal across the transition temperature. So that means at T equal to Tc, around at least T equal to Tc. And what is given is that we have a free energy. So, okay. So the question uses N as a normal. So let me use the same. So this is normal and this is S as a superconducting state. So given is that free energy difference between the normal and superconducting states is Hc squared T by 2. So this is the free energy difference. So if you notice this thing, this equation 1, let's say, the free energy for the normal state minus free energy for the superconducting state, it is always positive because mu 0 is something, a positive quantity always. And then Hc is also critical magnetic field, right? Whose magnitude is definitely always positive. And even if it, I mean, in other direction, you just flip the direction, Hc square is positive at least. So what does this mean is that Fn is greater than Fs. So this is also kind of sensible because normal state have if more, I mean, more free energy in the system, and superconducting state have lower free energy. So it's a kind of stable state. Superconductivity. So the system goes at low temperature, of course. The system goes to superconducting states by lowering its energy. So it's a stable ground state. So this only indicates that actually. So Hc form is also given, Hc of temperature. So Hc temperature is critical temperature at which the superconductivity of a material vanishes. So Hc of 0 and then 1 minus T square by Tc square. Okay, so what really happens is that suppose you have a superconductor and so this is along temperature and this is magnetic field. So you have a superconductor and you are applying magnetic field or H, let's say. So it is not that the superconductivity will be always there in the system. So after a certain threshold of magnetic field value, the superconducting material is going to lose its superconducting property. It is not going to, uh, I mean, having zero resistance state. So it can withstand. So this means that it can withstand superconducting property at certain up to certain magnetic field, even at a fixed temperature. So even if you are T less than Tc, and you keep increasing the applied magnetic field in the superconducting material, you will see after certain value of magnetic field, you just lost the superconducting states actually. This is again, if you, I mean, from a very heuristic point of view, you can think that once you apply magnetic field, the system acquires more and more energy, right? Basically, the magnetic energy part gets increased as with the increase in the magnetic field. Now, after a certain magnetic field, I mean, the electrons or Cooper pairs gets lost. They are not able to form a pair. Electrons are not able to form a pair and lower their energy from the normal states. And when this is lost, then superconductivity goes away. And this magnetic field at which, so this Hc is the magnetic field. So let me write explicitly. Lost also depends on temperature. So even if you are within the, I mean, below the critical temperature, so even if you are below the critical temperature, if you lower the, I mean, so if you are, so let's say this is Tc, and you are I mean applying the magnetic field. So you'll see that something like this curve will be there. So again, so this is HC actually, not H. So what this means, and this is HC0 at zero temperature. So what this means is at a lower temperature, the superconductor can withstand more magnetic field, and as you increase the temperature at lower magnetic field, the superconductivity gets lost from the material. Okay, so that is the physical point of this expression, this part actually. Anyway, so yeah, so that was the question. So we need to find this part. So this is equal to what? And C of n minus C of S equal to what? So these are the two questions. We need to find, uh, I mean, the difference between normal and superconducting state in the entropy and uh, specific it. Okay, so how do we do it? So we know from thermodynamics that for any material, the entropy is related to the free energy by this formula, right? Del F del T, where F is the again free energy at some constant magnetic field at some constant volume, right? So from this expression, you can directly just take, so sorry, Sn minus Sc, or yeah, S actually. So Sn minus uh, S, and you use this equation 1, you just take the derivative. So you need to take minus del T of F, and where F was given by this actually. So F of N minus F of S. So this means, so mu 0 by 2 you get common, okay, already have 2. Okay, so from here actually you can I mean determine. So why for, so you are already given Fn minus Fs actually, so no issue. Yeah. Okay, so from this I mean you just take the derivative and you get the answer, and the answer will be, I mean I am not going to write the answer, but the point I'm trying to make is that Sn minus Ss, so this part again should be positive. Okay, so so you'll find that the some combination will come, so that your entropy at the normal state, so yeah, your entropy at the normal state is going to be greater than the entropy at the superconducting states, and this is again physically sensible because since superconductivity is ordered states, so the particles are ordered. That means that the entropy of the superconducting states is lower than the entropy of a normal state. Okay, so this means Sn greater than Ss, ordered is less. than the normal state. Okay. And for specific heat, you will particularly find, okay, so how do we find specific heat? Again, the thermodynamics law says that you have del, so yeah, del U del T is the specific heat at some, let's say, constant volume. We are not changing the volume in the system. And then you can write this as del S del T, right? So then you will find Cn minus Cs. We can just take the derivative what we have found here, and then you get the specific heat. And what will be particularly, you will find that Cn minus Cs at t equal to Tc, you'll find something non-zero. Okay, so this is non-zero. So what this necessarily means is that there is a specific jump in the specific heat. So at Tc, so suppose, so this you are plotting versus temperature, this is specific heat. You are at some high temperature, and then at this temperature, let's say Tc, the your superconductivity in the material gets turned on, right? And you'll not, so what you'll not see is that this is not going to be there. Once the superconductivity starts, and there will be some jump, and then it will decrease. So this means that there is something happening here at Tc, and this is an indicator of second order phase transition. So I'm not deriving the, I mean, the solutions because it needs to be submitted, but I'm trying to give you the big picture and the physics point of view of the solution. Okay. So what this really means is that at Tc you are having difference between the superconducting state and the normal state. And because this C is proportional to second order derivative of free energy, this you can already see from this here, because S is also proportional to del F del T, right? We just saw here. So this one. So C is directly proportional to the second order derivative of the free energy. So that means if there is change in the specific heat, or for that matter, in general, any quantity where the quantity can be written as a second order derivative of free energy, and that is being discontinuous at the transition temperature, that means it's a second order phase transition. Okay. If it would have been the other phase transition where your entropy is discontinuous, then you'll see that I mean, then we interpret that phase transition as first order phase transition. Okay, so from this we can also, you can also verify that Sn minus Sc at t equal to Tc, you'll find it to be zero. Okay, once you I mean, once you derive this expression completely by taking derivative, you'll find that this is to be zero. Had it been non-zero, it could have been first order phase transition, but this is not the case. Superconductivity from the normal state to the superconducting state is I mean, second order phase transition. So the first order derivative of free energy is zero, whereas second order derivative is non-zero. So this, I think, the professors can ask from a, I mean, from a different point of view, that you show that superconducting transition is a second order phase transition. So this is one of the ways to see. So you need to remember this expression, let's say. So this first equation one, and then so that CV is non-zero, whereas S, or rather difference in CV is non-zero, rather, but S, difference in S is zero. So this kind of questions where we solve something in the assignment, but then similar question comes from a completely different point of view, or let's say from the point of view of the physics, a physical conclusion of the solution actually can come, because uh, I mean, in exam, there may not be exact repetition of the same questions, but just round about it. Okay, so this was the first question, and then second question was actually purely mathematical, I mean numerical. So second question is a superconducting material Sn is the superconducting material, has a critical temperature Tc of 3.7 Kelvin at zero magnetic field. So this Tc is at zero magnetic field. Now let me write H equal to 0. And then it has a critical temperature of 0.036 Kelvin at no. So this is Tesla. We have just a minute. Yeah. So you have a critical magnetic field Hc0 equal to 0.036 at t equal to 0. Yeah. So these are the two given, and find the critical field at 2 Kelvin. So we need to find Hc t equal to 2 equal to what? So this you can just find from the this equation itself. So Hc of t equal to Hc of 0 and 1 minus t square by Tc square. So you just put the Tc here, and then the temperature at which you need to find is 2, and then Hc0 is already given here. Okay, it's just the numerics. Okay, the second question is calculate the critical current. So this was A, and B question is critical current. So what is IC? And then what is the critical current density as well? So JC. Again, this is for a lead PB, and given that diameter is 1 millimeter, temperature is 4.2 Kelvin. Yeah, and then TC is 7.18 Kelvin, and HC is 6.5 times 10 to the power 4 ampere per meter. Okay, so what we really need to find is that this part. Okay, and this critical current density or critical current can actually be shown as related to I mean critical magnetic field as following 2 pi r Hc. Okay, so what we need to find is that Hc at temperature 4 point yeah, Hc at temperature 4.2 Kelvin. You need to find this, given that Tc is already there and then Hc is already there, and Hc is, so the question do not mention Hc at t equal to 0, so you need to assume that Hc given which is already Hc at t equal to 0. Okay, so you have Hc at 0, Tc you know, T already you know, so then you can find Hc at 4.2 Kelvin or T, and then you just I mean plug in there. So R equal to D by 2, and don't forget to everything, I mean convert everything to SI unit. And once you get the critical current, then critical current density is simple. JC is simply IC by pi r square, right? So yeah, this is the second question. And third question is find the susceptibility and relative permeability of an ideal superconductor. So we already found, I mean, just few minutes ago that chi is just del m by del h, and this is perfectly -1. And what we need to find extra is that uh, relative permeability. Okay, so what I was talking about. So what is mu r? So again, so we directly know that mu r is mu 0 1 plus chi, right? So given that you have chi equal to -1, it will be 0. So there is no relative permeability for an ideal superconductor. So mu r is 0 for ideal superconductor. Okay. Okay. So question 4. So any questions actually? Okay. So we have given so again some numerics. It just so the we have niobium. Critical field is there, 10 to the power 5 ampere per meter at temperature equal to 8 Kelvin is given, and it says that Hc0 is not there. But so let me actually write the problem, otherwise you will not understand. Okay, so the question is the critical field of niobium is 10 to the power 5 ampere per meter at T equal to 8 Kelvin, and this critical field of niobium at I mean 8 Kelvin is double of that at T equal to 0 Kelvin. Okay, so what we are actually having is that Hc of T equal to 8 Kelvin is double of Hc of T equal to 0. Okay, now we need to find the transition temperature. So Hc of T equal to Hc of 0 1 minus T square by Tc square. Actually, this should be, yeah. So we already have this. We don't even need this information actually. So we already have this Hc of 0 and Hc of 0 1 minus T already you know H square by Tc square, and from this you find what is Tc. Okay. Okay. So the next question is sorry. So draw internal versus external field for type 1 and type 2 superconductor. So this is just has been I mean this is just a plot you guys do. And then next question is also the same related to that. Assuming kappa is lambda by xi, where kappa is penetration depth and xi is coherence length, what is the approximate value of kappa c that differentiate type 1 and type 2? So basically, so you have kappa equal to uh, lambda by xi, or the other way around actually. Yeah, no, lambda by xi. So the threshold value is 1 by root 2. Okay, and this we can actually show from a very detailed calculation, but I don't know in this course this will be done or not. Yeah, okay. So the question 5a. So question 5a is again, I mean, we just use the electronic mass and then lights, I mean, velocity, electronic charge, and number density is given 10 to the power 22 parts semi-cube. Again, you need to convert to SI, and then find lambda L. Lambda L have that formula. London, I mean, length scale. And what is the temperature dependence of the second question is, so these are just numerics. You just put in the formula and be done. So what is the temperature dependence of the penetration depth? So as the temperature actually increases, the penetration depth also increases, because as the temperature rises, your superconducting states, I mean, becomes more and more weak. So the magnetic field can penetrate more and more. Okay. Okay. And then sixth question is derive the expression for coherence lengths of superconductors using Heisenberg uncertainty principle. And then what is the typical value of coherence lengths for a conventional superconductor? Okay, so uh, we need to find coherence length xi. So this is sixth question. Xi from Heisenberg uncertainty principle. So Heisenberg uncertainty principle is, so coherent length is the distance between I mean you can think of as a size of Cooper pair, let's say. So there is one electron, there is another electron, and then there is a phonon mediated interaction between these electrons, and then they kind of form this Cooper pair, right? But that doesn't mean ki one electron overlaps another electron. That this doesn't happen because there is a huge repulsion also. But in some materials, in fact, metals actually, not all metals show superconductivity. In some metals, there is a phonon mediated interaction due to the lattice, so that there is a effective attractive potential that develops between these two electrons. Okay, and there is certain distance between these two electrons, and when even when they form a pair, Cooper pair, so that distance characteristics length is called coherence length xi. Okay, now Heisenberg uncertainty principle says that delta x delta p is roughly, let's say, h bar, right, of the order of h bar. It has to be greater than equal to, but of the order of h bar for deriving this xi. Now, in this case, delta x is essentially xi, right? So what we need to find is this delta P. Now, delta P we can find that we have a characteristics temperature scale of KBTC because around Tc the superconductivity is there. So, characteristics temperature scale for the electrons or the Cooper pairs is KBTC, and then characteristics velocity scale is Fermi velocity because in the lecture itself you must have known or seen that uh, so there is some states below the Fermi C, right? So the electrons from below the Fermi C, and then there is a unoccupied states just above the Fermi C. So this is the Fermi energy, let's say, and characteristics velocity, Fermi velocity is Vf, and then there is a phonon mediated interaction, they form pair, right? So characteristics velocity scale or the energy scale is Fermi energy, and whose velocity scale is Vf. Now we know that P into Vf is the energy scale. Okay, so delta P. So our ultimate goal is delta P finding. So delta P times Vf, and it is the characteristics energy scale. Let's say delta E, and this delta E will be kBTC. So kBTC. So these are just scale arguments. Okay, none of that are exactly equal to. I mean, you cannot put equal signs anywhere. It's just scaling argument. It will give you rough estimate of the length scale or time scale or whatever you want to derive it. Here we are interested in the length scale xi. So that means delta P will be of the order of kBTC by Vf. Okay. So that means delta x from this part, or delta x equal to xi we can think of. So this will be h bar by delta P, and it will be h bar Vf by kBTC. So this is the I mean coherence length from the Heisenberg uncertainty principle. Now you can actually show from the BCS theory, detailed BCS theory, that this I mean coherence length is equal to h bar Vf kBTC. So there is a pretty good match between what we find from the uh, uncertainty principle and the detailed BCS theory. Okay. But there is only a factor of a, and a is less than 1, is almost equal to zero point 0.8 actually. So it is of the order of the same response you get, I mean same formula you get. Okay, so that was the question, and then how does the isotope effect indicate phonon mediated pairing of electrons that causes superconductivity? Okay, so this question is about isotope effect. So question 7, I think. Yeah. Okay, so the indication that the superconductivity is indeed phonon mediated, the isotope effect is one of the, I mean, very strong indication. Now, what we can actually found is that the change in, so suppose you take two superconducting material and two different isotope. Okay, so these are two different isotope of each other. Now you find so there we find that the critical temperature in between these two are slightly different. Okay, so they are not exactly same, and this delta Tc by, let's say, Tc, some mean critical temperature of this material or this material is actually proportional to delta M by M. Okay, so delta M is the difference in mass, ionic mass actually. So delta M is the difference in ionic mass. So difference between the critical temperature uh, with the, I mean, ratio with the critical temperature of any one of these material of the isotopes is actually directly proportional to the difference in the ionic mass between the two isotopes. So this directly tells us that superconductivity is somehow related to the lattice and then phonon dynamics, let's say. Okay, because the phonon dispersion, or let's say phonon mediation, is also intimately related to the ionic mass, because phonon are essentially I mean the waves that is created due to the oscillation of mass, I mean ions in the system. Okay, in fact, more precisely, if I want to tell that Debye frequency of phonon is root over 1 by m. Okay, so this is, so phonon's characteristic frequency is directly uh, or inversely related to the m square root of. Okay, so the next question is, so, okay, so so the next question is, let me write. So we have given this basic electrodynamic equation, and Js is the supercurrent density. So what we need to find is that London penetration depth. We also have given this identity. So for any vector A, curl of curl A is simply gradient of grad A. There is some, so this should have been, I think, divergence. Yeah. Okay. So what we need to find is what is the London penetration depth. Okay, this is the question, and given these are the basic equations. Okay, so this is also for a particular uh, structure, which is semi-infinite superconducting slab. Okay, so lambda L equal to, I mean, the expression for semi-infinite slab. So this we need to find. So this actually we can, so the question is sort of incomplete because it doesn't say semi, I mean, I should consider 2D or 3D or 1D.
You have to consider 2D only because slab is put it on the plane. That's why.
Yeah, 2D will be,
2D will be there, sir.
yeah, so then if I assume 2D, then
Because lab is we put generally in the lab in the 2D plain case, no, sir. It's
That's
not in
true.
the
That's true. So
yes, yes. We have to consider 2D only.
2D solution is actually analytically going to be difficult. I think it's not tractable if I not assume anything else as well. That is the
So
problem.
how it can be 1D, sir? Because we cannot put the slab in
That
1D.
that that I understand. That I understand.
Yes.
Yeah, I mean, so what you need to solve essentially is that so you so here is I think I've written something wrong. Curl of B. So this equation is wrong, I think, right? The question is this should not have been del V del T. It's kind of so this is basically the displacement current density. So this is actually kind of del E del T. Okay, so this is not del V del T actually. This should be del E del T. Yeah.
Yeah, this is daily delta.
Okay, so what you need to find is actually curl of I mean in end of the day we are going to solve this curl of B is some lambda square or lambda. It depends on how you call it, but B. So we need to solve this kind of equation actually. And what you can assume here is that del E del T is pretty much almost zero. Nothing is not no information is there. Anyway, this is displacement current, so we can uh, take it to be zero.
So it should be 0 because in case of semiconductor we cannot consider the electric field now. Yes.
Sorry.
Magnetic field is 0, no, sir. Del B by del T.
Yeah, this equation is anyway written wrong, I think, in the I mean question. So it should have been daily del T, but also that you
So
need to
we
consider.
don't have del T there, sir. We have already there del B del T, but in case of the superconducting state, it should be 0, sir.
Okay.
Yeah.
Yeah, I mean, I need to. So end of the day, we need to find something like that. That suppose if I talk about 1D, or even if I talk about 2D. So this is there is a cut at z equal to 0 plane, let's say, and then the material is already there up to z equal to minus infinity, let's say, right? So that's
Yes.
semi-infinite 2D.
Yes. Yes. Okay.
Now, so somewhere let's say here magnetic field is there, and then we need to find how much it penetrates in these materials. Now I'm not really sure that I can derive analytically for the 2D case actually. Okay, although it is clearly said that it's a slab, but for 1D case actually there is a pretty I mean easy solution. So if you have I mean hard boundary between these two, let's say not this is not semi-infinite, but if you have both the direction boundary, then something like this will look like. Okay, and similarly you can also find using I mean you need to just use the boundary condition that your B is equal to, so you will solve this kind of equation. Okay, and by taking curl of this you will get this basically. So so B equal to so here let's say this is B equal to B0, outside this is B0 applied. So then B equal to B0 at let's say x equal to minus a and plus a. For this case this is not semi-infinite. Now for semi-infinite in 1D we will have let's say uh, I can take at minus a itself. and then it goes up to infinity in 1D, let's say. So this is along the x direction, uh, extended up to infinity. So the boundary condition will be like that, that as you go, x goes to infinity, b will definitely be 0, and then at x equal to minus a, b is exactly b0, right? So this will be the boundary case, and for this case, for this finite case, these are the two, both of them will give b equal to b0 just at this point. So there is only a difference between this boundary case. So this is one and second, but I'll actually see if I can solve that for the 2D case. Okay, yeah. And anyway, if you have any questions, you can actually write to me at this email address. So maybe I'll come, but try to email me at least 1 day before. All right. So sunitd@iitk.ac.in. Okay, so the next question is, write down and explain first and second London's equation. So this just you need to write down actually. It has been discussed in the I mean class itself. But so first London equation is mu 0 lambda L square del Js del T. I think this is equal to electric field. Yeah, this I think this is correct. PDF of what? PDF of this. I mean, these notes are anyway going to be uploaded actually. Okay, and I'll just send the link, and it will be reflected in the NPTEL portal. Sorry.
Sir, I have one question from second lecture.
Second.
Can I? Second lecture taught by
Mm-hmm.
that I don't know. I not remember that stuff.
Saurabh
Yeah,
Basu, professor.
yeah, yeah. So minimum lower temperature Tc we can have the superconducting state. Yes or no?
Mm-hmm.
So above Tc, I mean that means high temperature.
Mm-hmm.
The material how it can be conducted by the all materials. High temperature पे कौन-कौन से material होते हैं मतलब we don't have the idea about the examples which are given by that theory.
Sorry, I didn't get your question actually. Can you repeat?
Sir, some theory is there that
Okay, some theory is there for superconductivity, right?
yeah, yeah, but above apart from that,
Mm-hmm.
for higher temperature, I want to say higher temperature, higher
So you mean to
temperature we
say high temperature superconductors?
yeah, yeah.
Actually,
So we don't know the phenomena what occurs between that those examples. That high temperature, how it can be a superconductor because we know that for the critical temperature it can hold below Tc.
uh, no, I think as far as I understood, so above Tc there is not going to be superconductivity for any material if the material is superconducting at lower temperature, meaning below Tc. Now there is a different section of superconductors which we call high Tc superconductors.
Yes.
That BCS theory actually cannot explain those things, and there is no comprehensive theory for those high Tc superconductor yet. Uh,
Yes, I want to study that one, but I didn't get the matter from any book, sir.
uh, yeah, I mean, this
Actually,
theory.
there is no research about that, sir. That much is stopped at that point, I think. because we can search about the high TC superconductors, but there is no idea it is, and no research about that, sir. I
No,
think so.
research is there. Research is
Mm.
going there. So the what really happens is that so BCS theory was developed around 1960s and so on, right? And this had been
Yes, yes, yes.
into the play, and it explains a lot of material superconductivity and so on.
Yes.
So it has been a part of textbook right now. So what
Right now it has been textbook, but there is no matter about the that high TCT.
no,
Yeah,
because the point is that there is no theory. I mean, there is
yeah,
no
yeah.
comprehensive theory that explains it. It's still a pretty much part of the ongoing research. We still do not
Mm,
understand superconductivity in two-state systems uh, very well. So,
mm.
unless there is a proper theory and understanding, you will not find it in a textbook, but rather you have to go to the research papers actually. Okay,
Yes, sir. Yes.
so that is the point.
Yeah. Thank you, sir.
Okay, uh, so this is the first London equation, and the second London equation is just Js supercurrent density equal to minus 1 by mu 0 lambda L square A. So A is the I mean the vector potential, so it's related as curl of A is magnetic field. Okay, so these are the two London's equation, and then what is the next question? So so this was 9. So the 10th question is find an expression for the superconducting density of state Ns of energy, and then plot Ns of energy versus E. Okay. So this Ns of E expression was actually explicitly derived, I think, lecture 3. So the derivation is just, I mean, you can follow from there. And the curve looks like something like this. So there is some threshold. After that, it actually exponentially falls off. Okay. And this is actually in units of delta. So E by delta. And delta is the superconducting gap. So in lecture 3, this was done kind of without telling or without fully solving the BCS solution. But in later lecture, I think in week 2 or week 3, there will be a full solution of the BCS theory using, I do not know, the second quantization notation will be introduced here or not. But yeah, I mean, we can solve the full BCS solution, of course, assuming that there is a potential which is only constant, okay, minus V0, let's say, and then 0. So, so with only this condition, we can actually solve. Rest of the cases, analytically, it is not solvable, at least. Numerically, of course, we can. So all of these expression and this, I mean, explanation of the gap equation and so on, it actually naturally comes. Okay. Okay, so I actually cannot fully solve any assignment question. So that has been the instruction from NPTEL. So even if I have solution, but I cannot solve fully. So yeah. So any doubt I can solve definitely, and anything from your side if you want. I mean, if you feel that any lecture or any part of the lecture uh, should be re-emphasized in the tutorial session, please email me at least a day before so that I prepare. Okay, so any questions?
No, sir. About the examinations, I want to tell you, sir,
Mm-hmm.
which is held on 29th of March. I think can we prepare the assignment questions or anything else other apart from that, sir?
No, mostly it will be from the assignment questions actually, but what the professor can do, they can tweak the questions a little bit. The one example I gave is that Uh, it's just that the first question was, I think, find the uh, difference between the normal state and superconducting state for the entropy for those.
Entropy and hyper. Yeah, yeah.
Yeah. So this kind
Specific.
of tweaking will be there, I think, or and some question will be just directly asked from the assignments as well.
Yes, yes.
Yeah.
So I refer only two books, sir. Pillai का एक है and that for solid state physics, and the other one is that for I don't know, but that is sufficient for that or no, sir?
Yes, yes. Yeah. Income will be a bit heavy, but yeah.
Okay, thank you.
So this is regarding submission of the assignment. Do we have to write it, take the picture, or do you have to type it and send?
No, no, no. You don't need to type. You just write it and make a PDF of all the pages and just upload.
Okay. Thank you.
Okay. So regarding PDF, yeah. So I'll upload this PDF to a Drive folder, and I think you got a mail from NPTEL or in the NPTEL portal also, the course portal. You'll have a I think Google Sheet link. So there every day's lecture link for the YouTube as well as for the drive of PDF notes will be there. Okay, I'll upload it by today night itself. Okay, okay. I think we can wrap up for today, and yeah, the next day we can continue with the solutions of assignment 2, I think. So when is the assignment submission date for this assignment?
Sir, it's 4th of February, sir, I think.
This is 4th.
2nd of February.
Yeah, yeah.
It's
No, yeah.
for first week.
2nd of February means
No, sir. 4th of February, sir.
okay. So even if whatever it is, 2nd or 4th, both. So before that, we are going to have another session at 30th January.
Okay.
Yeah,
Yeah.
yeah. The book.
Thank you, sir.
Okay. Create a WhatsApp group. There will be a better scope of discussion. I am not sure that everyone will to join WhatsApp or not, but I can send you your my number at least. That's it. Yeah.
Sir, please send on mail, sir, please.
Yeah, I think that is better. So I cannot send you guys individual mail because I do not have the email addresses. I can
Okay.
only upload things on the I mean Google Sheet. Yeah. There will be the link of this PDF as well as the YouTube video.
Yes. Okay, thank you, sir.
Yeah. Okay. Suggested book. Actually, there is not book at the very intermediate level. Income is the best book, but then it gets pretty heavy in terms of mathematics after maybe one or two chapter. Yeah, so I'll actually write the easiest book if I can find apart from income. Uh, at the end, so here I'll write the book actually, okay, and then upload. I do not remember there is I think one I mean book by some author which was a little bit easier than income. So I'll write
Sir,
book name here
sir,
and
there
then
is one book, sir. Sir, there is one book for solid state physics by S.O. Pillai. In that
okay, yeah,
detail, yeah,
SO
yeah.
Pillai is sort of it just discusses phenomenology, I think, right?
No, sir. Mathematical expressions are still quite lesser, but detailed information is there in that book.
Okay, okay, yeah, okay,
Mm.
okay. If you have any question, you just email me actually, okay? And I'll write the
Yeah.
book name, another book name I had, and yeah, and upload this PDF. Okay.
Okay,
Thank you
okay,
so
okay.
much,
Thank you.
and see
Okay,
you.
thank you,
Bye.
sir. Good night. Good night, sir.
Thank
Thank you,
you.
sir.